All right. So after DLVO theory, which I'm sure you enjoyed, we're gonna look at some 3D packing of lattices and some film formation of this. So this applies to soft materials. So we've seen, I think, like at 12 o'clock, you saw a picture of a colloidal crystal of hard spheres that organize into a nice FCC packed lattice. And those arrangements, they're quite intriguing because they have this periodic spacing and they have a color. They show iridescence. They show Bragg diffraction. And those materials are used for iridescent coatings. So if you have a nice shiny layer on your car, depending on the angle, you get a different color. Or they're, for example, used as a template to backfill. So one of those pictures, it was backfilled with titanium dioxide, and then you wash away the spheres, and you'll end up with this reciprocal continuous structure with periodic holes in it, which is used as a band cap material quite often in photonics, and which could form the basis of a solar cell type of arrangement. So that's what you can do with hard stuff. But what can you do with soft stuff? So that is what this is about. So there's quite some similarities, and soft stuff starts to do something different after a while. So film formation is essential for a lot of applications. For example, your waterborne coatings that you buy, but also for road adhesives and for paper manufacturing and for sealants and etc. Carpet backings. So it's a massive business. And basically what it comes down to is assembling and arranging particles, and then these particles, they fuse together, and then you'll end up with a coherent film. And sometimes you chuck lots of other stuff in there to glue everything together, and because the particles are soft, you can then refer to the particles as a binder. So it's big business, basically. So what is involved in this process of arranging the particles, packing them, and then getting the properties in the end material you want? So the film formation process is roughly divided into 3 stages. And here's a picture that basically tells you water loss as function of time. So after you've spread the film on top of the surface, and you just see what happens. And then initially what you get, obviously you have a dispersion of particles in water. So effectively you evaporate the water. Yeah. So typically you have 55% solid, so that's 45% water that you have to get rid of. So until almost all the water is gone, and you remember that in the ideal case, you can pack in an FCC or HCP lattice, and then you'll have 26% water left. So, and then what you then do is that you have to get rid of that, and that's not that easy because your capillary underpressures start to go up. And as a result of that, your particles will start to deform because they're soft. And then in the third stage, almost all your water is gone, and you might have a tiny bit of water left that you then have to get rid of. So you then, in stage 3, after your particles are deformed, you get interdiffusion of polymer chains. So in the end, all the boundaries between the particles are gone, and it's one macroscopic uniform material. That will be the ideal world. So let's have a look at this. And this is a video taken at BASF. It's slightly so first you have evaporation of water, and you can clearly see, that these particles, you get convective assembly. So here they slow down a bit, and you see they move. And there's movement, and packing, and this is obviously non-uniform. On the next slide, I'll show it a little bit in more detail. But you'll see that slowly but surely, there you go, at the edge, these particles pack quite nicely. And we'll come back to that, why this happens like this in a minute. So after that particular stage, so you see the particles moving towards the crystal edge, or towards the packed system. And you can think about this a little bit already, why that is the case, why it works like this. So you'll see here that they pack quite nicely, and you see here 2 crystalline regions on this image. So you'll see, you know, there's a bit of a grain boundary scar in between, which you could say it's a bit more amorphous. Yeah, so because obviously these things always are not perfect. You don't get one crystal. So here you have that system. And now the second stage is that you fuse these powders together, and here they cheat a bit. Here they put a heat gun on it. So what you'll see, and because of the heat gun, it kind of moves a bit, but effectively, see, there you go. So that normally doesn't happen. But what you'll see is that your boundaries start to disappear. Yeah? And in the end, you'll just end up with one completely smooth film. So that is the ideal case scenario on how film formation works.